Alrighty guys, so today we're going to do section 3.1, and I just have to start by saying that this is proof of how much I love and care about each and every one of you, because I feel like such an incredible tool right now making this recording. But you know, I'll do anything for my students. So here we go. We're going to start by watching this little video, so enjoy. So last chapter I mentioned that word derivative a bunch of different times. It's the slope of the tangent at a point. It's the instantaneous rate of change. It's just so long to say those, so we come up with a word and we call that word the derivative. So of course derivative is a long word to have to write out. So we have these different notations. So and I mentioned that in the video I think just now. So one way we can write the derivative of a function is like this. F prime of x. There's other ways to write it as well, the derivative. You read it f prime of x, but it means the derivative. You can also write it as dy dx. That's a different type of notation. You can do, if your function's called y, you could call it y prime. If it's f of x, you could do, oops, just kidding, d. I don't use this one hardly ever because it's just cumbersome. So it's d of f of x dx. Or instead of writing this, you could say you can just write d dx, and then you put your function over here. I use that one more often. Ooh, like that. Okay, so anyways, back to the definition of the derivative. And it says in here it's slightly different than what you've done in the past, and by slightly, I mean super slightly. So we have the limit as h approaches 0 of f of x plus h minus f of x all over h. So in chapter 2, we use this exact same definition, but instead of just writing a general x, we put in an actual value, and we called it a. Because before, we were finding the slope of the tangent at one particular point on a function. What this definition of the derivative does is it finds the slope at any point, slope of the tangent, on any point on the function. So maybe we'll even jot that down. The reason why it's slightly different is because this finds the derivative at a general point, x, rather than a specific point A. Specific point A. So that is the big difference between what we did before and what we're doing now. This basically gives us like a little formula so that all we have to do is plug in any value that we're interested in and we can find the derivative or the slope of the tangent at this point. Okay, so let's try doing an actual like number example. Let's say we want to find f prime of x, or the derivative of our function, for f of x is equal to f5x squared plus 4x. So again, it doesn't say at what point we're finding the derivative or the slope of the tangent. This is what's new. We're finding a general derivative. Alright, so we can go ahead and do our little calculations. If you want to try it on your own, you could press pause and do it. Oh, the power of the pause. You could figure it out first, and then you can go press play again, and you can see if you got it right. But we're going to use this definition. The limit as h approaches 0 of f of x plus h minus f of x all over h. And we're going to use our actual function, which is this one right here. So we're going to take the limit as h approaches 0. Our function is 5x squared plus 4x. And what are we going to plug in first? Let's even switch colors. We're going to plug in x plus h. So we'll plug in x plus h and x plus h. Alright, good. And then we have all of that, and then we're going to subtract f of x. So f of x is just 5x squared plus 4x. And then all of that gets put over h. Alright, so now it's just a lot of algebra. So let's see what we can do to simplify. So we're going to have 5, no killing any bunnies or puppies or kittens. I almost said chickens. Don't kill them either. We have that, and then plus h squared plus 4x plus 4h, and all of that. Ooh, hang on a second. Whoa, Mrs. Kelly, pay attention to what you're doing. There we go. We don't need that little one right there. Why is that not erasing? I don't know. Well, you know what? We'll go like that. Ha! Solve the problem. And then careful right here with your negative sign. Make sure that you distribute it through to both. So it's minus 5x squared minus 4x. And then put it all over h. So we got the limit as h approaches 0. And then, hey, I need a little bit more space here. So let me add in. I'm not sure how in the world they thought we were going to be able to fit that there. Okay, good. Alright, so what am I trying to do? This is a disaster. I can't just plug in 0 for h. So, oh, there's weird things going on now. Hold on. Okay, there we go. Alright, so I need to do some magic simplification on the top. Lots of algebra. So what do we have? We have 5x squared plus 10xh plus 5h squared plus 4x plus 4h minus 5x squared minus 4x all over h. Okay, so remember what our goal is going to be here. It's going to be to try to factor in h out of the top. So right now we've got, oh dear, what just happened? We have a bit of a disaster in that we don't have the entire top in terms of just h's. We've got some x's and whatnot combined in. So hopefully we're going to get some things to cancel. So let's see. Oh, look at that. We got a positive 4x and a negative 4x. That's good. Ooh, 5x squared. Oh, positive 5x squared, negative 5x squared. Now look at what's left. Every single term has a factor of h. So what can I do? Yeah, that's right, kids. I can factor out an h. So I factor out the h, and I'm left with 10x plus 5h and plus a 4, like so. And then it's all over h. And sure enough, I can cancel out those h's. Is it safe now to plug in h is equal to 0? Sure, so I'll do that right there. H is equal to 0. And then what am I finally left with? 10x plus 4. And that, kids, is the derivative of my function at any point. And then notice my answer is a function. It's not just a number like we had before, back in good old chapter 2. But see, here's the magic part of that all, is we have a function, so if we want to actually figure out the value of the derivative at any point, here's all we have to do. We would just plug in the value. Say I'm interested in finding the derivative of my function at 1. Well, that means I just take my function and I plug in my derivative function and I plug in 1. And what do I get? I get 14. Oh, the slope of the tangent line at x equals 1 to this particular curve is 14. Pretty steep. Okay, say I wanted to find the derivative at 0. What's going on? At x equals 0, I would just plug in 0, and when x equals 0, the slope of the tangent line, the derivative, is only 4. See? So we can keep going and going and going. It's kind of handy instead of having to do this whole crazy process over and over and over again with different numbers, like we were doing back in chapter 2. We've got ourselves a little shortcut. So I'm sure you guys remember back in chapter 2, oh, so long ago, that we had two different ways of finding the derivative, the slope of the tangent, right? So the other way was to do f, well, this is our new notation, but if I wanted to find the derivative, let's say at a point A, then I would take the limit as x approaches a of f of x minus f of a all over x minus a. So here, this is the derivative of f of x at an actual value, x equals a. But what we're going to do a little bit differently, oh, maybe we'll even write that in there, that this is at a specific value. So what we'll do a little bit differently this time is that we're going to leave a in our whole entire limit problem, and we'll see what happens. So we have the limit as x approaches a, and then we'll use that same function that we just had before. It's f of x, so it's 5x squared plus 4x minus f of a, so I'm just going to plug in a for all of my x's. So these two on the top look almost exactly the same, but they're not, all over x minus a. Okay, so again, this is just f of x minus f of a, meaning plug in a for x, all over x minus a. So I just need to do some algebra. That's going to give me 5x squared minus 5a squared. Oh, magic, Mrs. Kelly. What did you just do? I did that. And then, trust me, there's a method to my madness, plus 4x, and then watch out, minus 4a. So I distributed and I just rearranged my terms a little bit. Why would you do that? Well, what do I have right here? I have the difference of squares. If I factor out a 5, I'm left with x squared minus a squared. That's going to help me with that on the bottom. Plus, what can I factor out of these two terms? Yep, a 4. Good job, kid. X minus a all over x minus a. Oh, we're almost there. See it? See it? I have an x minus a here. Oh, it'd be so nice if I had an x minus a there so I could factor that out and then cancel with what's on the bottom. So let's make that happen. Difference of squares, x plus a times x minus a plus 4 times the quantity x minus a all over x minus a. Yahoo! I've got a factor of x minus a here, here, and here. So that means I can factor an x minus a out of the top. So let's do that. Let me make some room first. Oh my goodness. Okay, I'll do it over here. So oh, red. Don't want you. Okay, so if I factor in x minus a out of the top, what's left behind would be 5 times the quantity x plus a plus 4. And then it's all over x minus a. So, boom, boom. And now, oh, I think I've lost my little limit as x approaches a. So that means I want to make x get closer and closer and closer to having the value of a. So before, if a was like 2, then we would have just plugged in 2 everywhere. But now we're not going to plug in 2, we're just going to plug in a. So if I plug in a right there, that's going to give me a plus a right here. This is 2a. So 10a plus 4. But remember, I'm trying to find f prime of x, a, at any value. I can change that back to an x. And so that's it, guys. My derivative of my function at any value x is 10x plus 4. And that's exactly the same as we got before. So hip hip hooray. Okay, so here's what I want you guys to do. Press pause, and I want you to see if you can use this f of x minus f of a. Oh, actually, you know what? You're going to need to do it both ways. Yeah, I want you to do it using both definitions. But maybe you can try doing it all by yourself. And then you can press play and see if you get the same answer as I get doing it both ways. Alright, so using definition number 1, let's actually find the derivative of f of x, which is 1 over x squared. Alright, so we'll start by using the first definition, which is the one that has the h in it. Doesn't really matter what the order is, by the way, on that. Alright, so here we go. The definition is f of x plus h, let me write this on the top a little bit, minus f of x all over h. So this means take our function and just plug in x plus h. So what was our function? Our function is 1 over x squared. And then over here, it's 1 over x squared. I keep it. In the first set of parentheses, I need to actually put in x plus h. I substitute that in. Alright, so I have everything set up, so now what I need to do is I need to simplify this. This one's tricky because it's a fraction. And in order to actually simplify fractions, or add or subtract fractions, I need a common denominator. So what's the common denominator going to be? It's going to be this times this. They have no factors in common. So that means I need to multiply the top and bottom of this one by x squared, and then I need to multiply the top and bottom of this one by x plus h squared. Alright, this looks horrid, but it's going to be okay, nobody panic. So here we go. On the top, we're going to get x squared over our new denominator, which is x squared times x plus h squared. By the way, if any of you guys were thinking, oh, well, you need to FOIL this out right there, ooh, you could, it wouldn't be wrong, but boy, it would sure make this problem look a lot uglier, so I would not recommend it. Alright, over on the other side, 1 times x plus h squared is just x plus h squared, and then you have x squared times x plus h squared. But wait, that's just the numerator. You still have all over h, and I'm finding that limit as h approaches 0, right? So same problem. Can I just plug in a 0 right here? No. So I need to simplify and do some magic on the top. So what can I do to actually simplify this out? Well, I want to see, first of all, if maybe now foiling on the top here would be helpful, and I think it would be. So let's do it. The top of this comes out to be x squared minus, alright, we're going to FOIL, x plus h squared is x squared plus 2xh plus h squared. The denominator is still x squared times the quantity x plus h squared. And we're going to leave that one alone, and then it's still all over h. So, here it is, the magic. I want to make sure my top has everything only in terms of that have factors of h's in them. So now, when I distribute that negative through, magic happens. I get x squared minus x squared minus 2xh minus h squared. All over, and then here's where I'm going to simplify life a little bit. Dividing by x squared times this whole quantity blah, and then dividing by h again is the same thing as dividing by x squared times x plus h squared times h. Alright, if that was a little confusing to you, just remember, dividing by a number is the same thing as multiplying the numerator by its reciprocal. So see how here I'm going to wind up with h times all of this. Okay, now I've made a mess of this, but that's the idea. I just multiplied the whole numerator by the reciprocal of h, which is 1 over h, and that's how we wound up with that down there. Okay, so, ooh, that was fancy. Okay, so anywho, back up to here. So we got that and that to cancel out. What's left on top? Oh, look at that. It has only factors of h. So if I factor out an h off the top, then I'm left with negative 2x minus h all over the bottom, x squared times x plus h squared times h. And now, sure enough, my factors of h cancel each other out. And remember what I'm trying to do, I'm finding the limit as h approaches 0. So now, is it safe to just plug in 0 for h? Absolutely. What's left on top? Negative 2x. What's left on bottom? Well, it's x squared times x plus 0, so that's just x. Oh, x squared again. It's x to the 4th. So I can cancel out an x, and I get negative 2 over x cubed. And that's it, guys. That's the value of my derivative of f at any point x. So it's negative 2 over x cubed. Yay! Alright, so we're going to do that whole problem again, but this time we're going to use the second definition because I told you guys to do that. And maybe you've even already done it, and now you're just checking to see if it's right. I already know what the answer should be, right? I should get the exact same thing. I should get that the derivative of f of x is negative 2 over x cubed. So let's see if we can make it happen using definition number 2. Definition number 2 is f prime of a is equal to the limit as x approaches a, and it's going to be f of x minus f of a all over x minus a. So my function was 1 over x squared, so f of x is 1 over x squared. F of a would be 1 over a squared. And so now my job is going to be to simplify this down completely so I can just plug in a for x. So it's going to be basically the same process. I need a common denominator, which is going to be multiplying this one by a squared over a squared, multiplying this one times x squared over x squared. My common denominator is just going to be the two denominators multiplied together. So my first fraction is a squared over x squared a squared minus x squared over x squared a squared, and then all over x minus a. So, bring that down. I want to actually subtract the top, so I have a squared minus x squared all over the same denominator, so I can put it just on the bottom, x squared a squared. And then you know what, right here I'm going to do it. Dividing by x minus a is the same thing as multiplying by the reciprocal of x minus a, which is 1 over x minus a. So I just need to multiply all of that. So on the top I get a squared minus x squared. On the bottom I'm going to get x squared a squared times x minus a. Alright, so, oh, look at the top, we got the difference of squares. So let's simplify that. I have a plus x times a minus x all over x squared a squared times x minus... Aw, man, do you guys see why I'm all manning? Because remember what I'm trying to do? I'm trying to just be able to plug in a for x, but if I do that right here, I'm going to get 0. So I was hoping that I'd have the same factor on the top as on the bottom, and I almost do. I almost do. This is just about the same as that, but not quite exactly. See how it's a minus x and x minus a? 5 minus 2, 2 minus 5. Are they the same? No. So I'm not ready to just cancel those out yet. I need to factor something out of here so that it's going to be exactly the same as this. I need my negative x to become positive x, and I need my positive a to be a negative a. So what can I factor out? Oh, that's right. Good job, kid. You want to factor out a negative 1. When I do that, if I suck a negative 1 out of here, then this becomes negative a plus x, or I can write x minus a to make it look nicer. And then everything else just stays exactly the same. A plus x over x squared, a squared times x minus a. But the good news is now I can cancel those out, and then I can actually find the limit as x approaches a. So all I want to do here is actually plug in a anywhere I see an x. So if I do that, I plug in a here. What am I left with on the top? Negative 1 times a plus a, or yeah, which is 2a. So it's negative 2a over, and then if I plug in a right here, I want to do that right here, I get a squared times a squared, which is a to the 4th. Hey, that looks familiar. That's kind of what we had before. Remember that a canceled out with 3 of those, and I get minus 2 over a cubed. So, I think I'm almost done. I now want to change everything back into x's so that it's in general terms. So I have my derivative of my function, f prime of x is equal to negative 2 over x cubed. And I just changed the a's to x's because this is at any point a, which is means the same thing as saying at any value of x. So yay, we got the same thing both ways. We're super happy about that. So now kids, I'm done yapping at you, and that means that you get to start working on some homework problems. So here they are right here, or at least the beginning of them. Find f prime of x for each one of those. And so as to not torture you too much, why don't you do half using the first definition and half using the second definition? Well, there's an odd number, so 2 and 2, and then you can choose whatever on the third. Alright, hope you guys enjoyed my little video. Again, can't believe what a tool I feel like, but hopefully it was helpful. Alright,